Quick notes, this webinar will be recorded and available for download. Please type your questions in the text box and we will answer them at the end. And now I give you Roger McAteer of Wilson Industries.
Good morning. Today we are going to do a review of ESD control training. There is a document, an international standard referred to as the ANSI ESD S20.20, which had a revision in 2007 and has required initial and recurrent training for ESD awareness prevention. This is commonly used with this PowerPoint as well as an ESD awareness guide sold by Desco Industries. The ESD control plan is designed around what is referred to as the 100-volt human body model limit, which was selected by the ANSI S2020 as a baseline for susceptibility issues as the threshold for the large majority of ESD products on the market have sensitivities greater than 100 volts. This gives a baseline of protection in excess of what typically would be required in electronic facilities today. As always, safety first is the most overriding condition. Anytime operators might be working with live circuitry or anything that would exceed 250 volts AC, the personal grounding should not be used, but rather ionization for static control. Some of the basics. Static is an electric charge at rest. Tribal charging generates static electricity. So anytime two surfaces contact and separate, electrons transfer from one surface, causing an imbalance. Positive and negative charges both can cause ESD damage. Electrostatic generation. This can happen with any two materials coming together and separating. It can be plastic and plastic, two insulators. It can be metal and plastic. Walking on carpet is a very common static generator. Plastic tends to have positive charge and more dangerous for higher levels of charges, but both positive and negative can do damage. The size of the charge also can be, depends on the materials that contact and separate, how much friction time, the relative humidity in the atmosphere, and also they can accumulate if not controlled on conductors. The charges, when there is a discharge, this is the function of an imbalance seeking to neutralize itself. This discharge energy causes heat, and heat is what causes the damage. It's similar to a micro lightning bolt. Lightning is a very large example of static electricity, as well as the zap you feel from walking across a carpet and then touching a doorknob. To feel a discharge or the shock, the voltage must be about 2,000 to 3,000 volts, and to see it, about 7,500 volts. ESD control is necessary to prevent innumerable little lightning bolts or ESD events from occurring. 25% of unidentified electronic failures are typically a result of ESD. This is some typical examples. Walking across a carpet, you can get up to 35,000 volts. Walking over untreated vinyl floor, up to 12,000 volts. And vinyl envelopes or plastics at the workbench with instruction sheets, up to 7,000 volts. And even an operator just moving around on his chair at a bench can generate as high as 6,000 volts. Unwinding regular tape, also at a workstation, can generate up to 15,000 volts. In today's electronics, even less than 100 volts can damage a component. We have some that are now as low as 10 static volts sensitivity. So one of the reasons people say is, why so sensitive? As devices have gotten smaller and smaller, the gates and spacing dimensions have been reduced. These, and also the voltage to operate the components has been reduced to make smaller power supplies to drive the devices. So classifications that came to bear on the human body model, which is operators or people, the charge device model, which would be insulators or devices at a workstation, and the machine model, which would be automating machines that are sometimes used in electronic assembly. The classifications have been set up currently as Class 0 from 0 to 249 volts, Class 1 250 to 1999, and on up. We do now even have people discussing Class 00 and Class 000 so as to get down to 0 to 50 volts for Class 000 device. So what we need to do is understand how we need to control static electricity and protect our devices at the workstations. One, we need to have a company have an ESD control plan, which would typically be a written control plan. We need to identify an ESD protected area or an EPA. Sometimes the people will identify different classifications for different EPAs. The recommendation by the S2020 is that we classify everything as Class 100 volt devices and go into Class 0 control for all locations. When we put a control plan together, it needs to have facilities, your suppliers, any contract manufacturers, all of them need to know the standards and be part of your ESD control program. Controlling ESD, we need to consider two different items that would potentially be at a workbench: conductors and insulators. Conductors are good and bad. Examples of conductors are metals, some carbon devices, people. It's an item where electrical current flows easily, which is a good aspect of it. They can be grounded, which is a good aspect of it. But also, if they are not connected to ground, they can become isolated conductors and hold the charge, and that is a bad feature. Insulators, or non-conductors, are items like plastic, paper, clothing, product enclosures that are not metal. These are items that electrical current does not flow easily and they cannot be grounded. Plastic cups or water bottles, other items such as that cannot be grounded and cannot conduct a charge away. When we have damage caused by ESD, there are two potential conditions. One is a catastrophic failure, and the other is a latent failure. Contrary to how it sounds, a catastrophic failure is actually better than a latent failure in that the catastrophic failure is found in the factory, detected, repaired. It increases the cost of manufacture and getting the product out the door, but it goes out as a completed quality piece. The latent defect is the most expensive because it potentially passes inspection, goes out, and you have a premature field failure. So the items that suffer a latent failure pass inspection, go out to the customer, then all of a sudden there's some field failures, premature field failures, and this can be very costly in product returns, repairs, warranty costs, and lower customer satisfaction. One study showed the progression where if you have ESD damage to a device, you may lose a $10 device. If it has been processed into a board, it could cost you $100. And if you put it into a complete system, it can go up as high as $10,000 for that static control failure. Many people consider latent defects similar to germs as a hidden enemy. These are things that cannot be felt, cannot be seen, and cannot be detected through normal inspection. These are a couple examples that are under super high magnification where you can see an actual ESD event. This is not staged. This is an actual man who had a charge, and it was showing it going to the component. This is one of those little micro lightning bolts at 10,000 time magnification, which is one of those little micro strikes you get that does the damage to the metal component. This is a side fracture off a trace. again, at a very high magnification at 5,000 times to see the damage that can be done. Germs and ESD, like I said, have been compared much the way you cannot see germs or feel any difference in anything. You always know that you'd want to control and have a sterilized environment if you were going to have surgery. The same thing would apply with regards to static control. You need to have the protection in place even though you cannot feel or see any static control damage. The front line of defense is always the personal grounding device, which would be the wrist strap, which should be worn snug around on the skin, should be clean, and the cord connected to ground. Foot grounders are an alternate system where it is strapped on the heel of the shoe. The grounding tab is stuck under the foot. You would wear one on both feet, but it also needs to be in contact with some ESD grounded flooring system, either ESD carpet, ESD tile, ESD paint, ESD epoxy floor, but you need a floor system in conjunction with heel grounds. Personal verification is required of these devices in order to make sure they're functioning properly. So the wrist strap must be tested by a testing system at least daily. Unless continuous monitors are used. Continuous monitor is a device that would be right at the workstation. It's wired to ground, and it monitors the work table mat as well as the wrist strap being worn properly and functioning properly. Foot grounders must also be tested at least daily, preferably twice. The prevailing thinking is that you would come to work, put on your heel grounds, and you would test when you leave the EPA area, say for lunch. A lot of people take the heel grounds off, so then it would be required as you re-enter the EPA to test your heel grounds again. It's required to have a mandatory written log logging everybody doing their testing. One of the second lines of defense is to have a dissipative work surface at our mat. That would be grounded, so this would keep our operator at 0 voltage with the wrist strap being grounded and the work surface being grounded via a ground cord to ground the ESD mat. Conductive floor mats are also an available option for standing tasks where they will be grounded in conjunction with the table mats. There are two surface materials that are used for either flooring or table mats, dissipative and conductive. We would always want to have dissipative material as our work surface area or anything that would have intimate contact with a electrostatic sensitive device or component. You want to keep the area clean as well as clear of any insulators. The ground cord should be visually checked occasionally. And ESD hand lotion can help sometimes enhance the contact between a wrist strap and the operator to make a quality ground. Sometimes at a workstation we may have some insulators that cannot be eliminated or replaced. These are called process essential insulators, and when that is the case, we would then use ionization to neutralize the charges. A couple of different types of ionizers. The benchtop ionizer is probably the most popular. It's placed on the bench, pointed at the area where the neutralization is needed. Sometimes there are processes that need a air blow-off gun, and if you're doing it to ESD-sensitive devices, you would want to have ionized air coming out of that because the moving air will cause the friction and a static charge. Overhead ionizers are used for some of the larger bench areas. These all today have auto balance systems that they monitor themselves and will alarm, but they do all require maintenance in cleaning emitter points and monitoring controls. When we have the opportunity that we need to move product from an ESD protected area, we will always use shielding, which generates the Faraday cage effect. The two most common used for moving products to and from an ESD protected area would be a metallized shielding bag, not the ESD pink bags or low-charging poly bags, but it must have the metal shielding feature, or covered ESD totes, either conductive or dissipative totes in a box with a lid. The electrostatic shield is what gives a protection from any discharge. When the item is placed inside a metallized bag and the bag is closed and sealed, the operator can then disconnect from the wrist strap, carry it, transport it, place it in inventory, or move it to its next task. But before the bag is opened, it should be at an ESD protected area. The operator would have a wrist strap. As soon as they would touch the bag, any charge on the outside of the bag would be brought down to 0 voltage and would be safe to remove the device. The same would apply for the ESD tote. An operator at an ESD protected area with a wrist strap would be able to place items inside the tote. Once inside the tote and covered, you would be able to disconnect from ground, take that tote, take it to an inventory area or its next task, and so long as before it's opened again, it is done at an EPA with a grounded operator. The other dimension of shielding that is found is ESD garments, which has the same shielding effect for clothing. Clothing are insulators, and if they have a charge, it will not be reliably brought to ground via the wrist strap. So the ESD garment does a shielding factor for the operator's clothing. The main feature that we have for our ESD protected workstation is going to be grounding all conductors, including people, removing any insulators or neutralizing the process with an ionizer to give a complete ESD controlled workstation. So it is imperative to have people understand that only trained or escorted operators are allowed in the EPA. All of the guidelines that are set up in the company ESD control plan need to be followed. Testing needs to be done daily, written logs to verify this testing, and shielding is always used when products are not grounded. We're open to any questions.
Thank you, Roger. If you have any questions regarding ESD, you can contact your Philadelphia area ESD contact, John Tharp, at Danaher Electronics, at danaherelectronics@verizon.net. You can also go to Wilson Industries at wilsonindustries.inc.com. And for information on Electrosoft Incorporated, you can go to www.electrosoftinc.com. Everyone listening to this webinar will get the chance to have an on-site ESD survey. We will contact you if you've signed up for the webinar. If you have not, please send us an email at info@electrosoftinc.com. This concludes the webinar.